All right. Thanks everyone for coming to the random testing session at the Haskell Symposium. Our first speaker today is going to be Edsko de Vries, talking to us about shrinking.
Thank you very much. 11 years ago at the Haskell Symposium in Denmark, Copenhagen, Denmark, Koen Klaassen presented a brilliant paper, a functional Perl. At the time, QuickCheck was able to generate functions, but not show them, never mind shrink them. And Koen Klaassen showed how to do this. It's a great paper, it's mind-blowing, I recommend reading it. But what Koen did in his presentation, he started with a demo of a simple property that uses a function that's being generated and shrunk. And since science is all about repeating things, I want to show you a similar demo before I move on to anything else. So here is a simple property written in the language, in the library called Falsify. So in this property, what we're doing is we're generating a random function from a list of word 8 to a Boolean by calling a function from the library called fun, which takes as argument a generator for the results of the function. In this case, we're generating random Booleans. The false argument there, by the way, is saying we're going to shrink towards false. And then we're going to assert about this function that if we apply this function to the list 3142, we should get the same answer as when we apply it to the list 1618. Right, so this property is saying that for any function from a list of word 8 to bool, that function should give you the same answer for these two lists, which of course is clearly nonsense. Right, so we should have a counterexample to this. So when we run this in Falsify, then we're going to get a counterexample. And in this particular case, the counterexample that we got was a function at the bottom here, this generated line here. And this function says we're going to return true for the list 1618 and false everywhere else. Right, so this is an obvious counterexample to the problem. And it's a nice, beautifully minimal counterexample. And if we run this again, we might get the same answer, or we might get one different. In this case, we happen to get a different one, which is a function that returns true for the list 3142 and false everywhere else. Right, so these are the only two counterexamples you're going to get. Right, these are the only minimal counterexamples to this property.
Is this what QuickCheck does today?
This is similar to what QuickCheck will do today, yes. Except this is a Falsify what you're looking at, but yes, QuickCheck will do this too. And Koen showed how to do this in QuickCheck. But I did not write a shrinker. Right, that's the point. So Koen showed how to write a shrinker for this. The point of Falsify is that you're not going to write shrinkers. You get shrinking sort of implied in your definition of a generator.
Failed after 59 shrinks.
Yes. Yes, indeed. So this is how it works in general, right? When you do property-based testing, you generate some large counterexample, you're going to get lots of unnecessary detail, then you throw out the unnecessary detail, and then you end up with the counterexample that you're actually interested in. And in this particular case, the function that we're generating is infinite, and so it's very important that we shrink it, because we don't want to show you an infinite function. It's infinite because it has a value for every potential input, right? Okay. So I want to talk about Falsify, and I'm going to do this by placing it in context of the existing libraries for Haskell, in particular, of course, the granddaddy of them all, QuickCheck. And so in QuickCheck, how do we do property-based testing? Well, a generator in QuickCheck is a pair of two functions. Right? We have a function that produces a value from a random number generator, and then, like we just said, that probably, if we find a counterexample, that counterexample probably has lots of unnecessary detail. And so we need to shrink it, right? We need to come up with smaller counterexamples. Now this works quite well, but the problem with this definition is that it has very limited composability. So in particular, for example, we cannot give a functor instance. Right? For a functor instance, we have a function from A to B, and a generator for an A, and we need to give you a generator for a B. Now the generation part is easy. We just call the generator for an A, and we call our function to get a B out of it. Easy enough. But the shrinking is impossible. Right? We have a shrinker, a function from A to list of A, and we need to produce a function from B to list of B. So we have a B, but we can't apply the function. We would need a function from B to A before we can call the underlying shrinker. Right? So this is not definable. Now, this is a well-known problem, and in Cubic QuickCheck, introduced a long time ago, they solved this problem by using integrated shrinking. And in the Haskell world, this is most well known from the library called Hedgehog. And in this case, a generator is a function from a pseudo-random number generator as before, but now to a tree of values. Now the root of this tree is going to be the original value, right? The original produced value, and then values further down the tree are shrunk values. So this has an obvious functor instance, right? We just map the function over the tree, very easy. And it also has a very good applicative instance. So for example, if the tree on the left here, this 2, 0, 1, 0 tree, that might be a generator that produces a 2, which can shrink to a 0 or to a 1, and that 1 can shrink to a 0 again. Right? And then maybe you have another tree, we produce a B, which can shrink to an A, and then we can pair this up very easily. Right? How do we pair them up? We just take the roots, and then we either shrink the value on the left or shrink the value on the right. Very simple. So applicative instance works very well. Where this falls down is in a monad instance. And the monad instance is important, right? Because when we're generating arbitrary values, we very often need monadic bind. For example, when we're generating a random list of values, we need to pick a length, and then depending on the length that we choose, we need to produce that many elements. Right? So the effects that we need clearly depend on values that we generate earlier, which is clearly monadic bind. And so in the hedgehog world, what does this look like? Well, we might have this tree, right, the 2, 0, 1, 0 tree that we had before. That might be our length. And then you can imagine that for every length that we pick, we have a tree of potential trees, a tree of potential lists of that length. Right? So we have a tree of trees, which is that picture on the left here. Now the problem is, how do we flatten this tree? And the answer is, we basically cannot. There is no good way to do it. And picture B here is the normal way that people do it. What you should note about this picture is that when we go, for example, from BB to AB, right, so we shrink one of the characters, we never go back anymore and shrink the length of the list. And this is a general property of integrated shrinking. Like every monadic bind introduces a cut point, right? We shrink on the left, we make a decision. Once we start shrinking on the right, we never go back anymore and shrink on the left. And if you think about it, this actually makes sense because monadic bind, we have a function on the right-hand side. Right? So we have a generator, produces a value, which we can shrink. After we apply our function to a shrunken value, well, then we can start shrinking on the right. But if we now go back and shrink on the left again, the only thing we can possibly do is reapply our function and start all over again. Right? So this is inherent to this approach. Now the Python library called Hypothesis showed us how to do this in a different way. And in the paper there's a detailed comparison to the Python library. I'm just going to focus on what Falsify does here. Now the key idea from Hypothesis is that we're not going to interpret a pseudonumber as a function, a generator, as a function from a pseudo-random number generator. Instead, we're going to unfold the generator of pseudo-random numbers, get samples from this generator, and then we're going to parse these samples to produce values. Right? And we saw this earlier in the talk about internal shrinking with bidirectional parsers yesterday, I think. So this is the same idea here. Now when I first heard this at Haskell'23 last year, I thought it was completely bonkers, but actually it works surprisingly well. And so what we do in Falsify is we don't unroll this as a stream of values. Instead, we unroll it as a tree, an infinite tree of values. Right? So if you have a pseudo-random number generator, you can split it right, into two independent generators. Those are your two subtrees. Or you can draw one value from the generator. That's the value that's there. Right? So the idea is that you're either going to use the sample or the two subtrees, never both. Now this tree is always infinite, conceptually at least, but we have a finite representation of the minimal tree that is 0 everywhere. It's an important optimization, but I'm not going to focus too much on it. But you can think of this as an infinite tree, and so we can have a view pattern on this that says, well, any tree you can think of as an infinite tree, we can always pattern match on it. If it happens to be the minimal one, then the sample you get out of it is 0, and the two subtrees are also 0. And I'm going to use it.
Should I think of it as just a random number generator, but splittable?
Yes, yes, yes. A splittable random number generator. Yes, absolutely, yes. Okay. So then as a first approximation, a generator is simply a function from one of these trees to a value, right? A parser of this tree to a value. Now that doesn't quite work, because these trees are infinite. Right, so if you think about it, when I'm shrinking, what I'm going to do is I'm not going to shrink the resulting values anymore. I'm going to shrink the input to this function. Right, I'm going to shrink the samples that we get from the random number generator. That's the whole point. So you're not going to write a shrinker. You're just going to reapply your function after shrinking values in this tree. But this tree is infinite. Right, so if I'm shrinking by shrinking this tree, I can always find a value somewhere to shrink, which is irrelevant to the function that I'm using because it might not even look at it, and so shrinking would not terminate. Right, and so we need to know where in the tree that we're shrinking. And so we're actually not going to use we're going to use this definition instead. A generator is a function that takes a sample tree as input and gives you a value along with the possible ways to shrink this sample tree. And the main idea here is that this is primarily so that we can sort of know where in the tree is useful to shrink. And so, for example, here's the most primitive generator of them all. It just draws one value from this tree. Right, so what do? We pattern match on this tree. We use this inf thing to always pretend that this tree is always infinite. The value that we return is just the value at the top of the tree. And the only thing that we can shrink, we just replace the value at the root of the tree by smaller values. Right, so this is like binary search or something like this, like the normal way that you might shrink samples in quick check or something like this. Okay.
So the subtrees are just completely ignored here?
The search tree is completely... The subtrees, yes, the subtrees are completely ignored. Yes, the only value that is relevant to the primitive generator here is the value at the root of the tree, and so the subtrees we just leave alone. Yes, correct. Okay.
So I'm still not getting it. So the subtree's returned, the S tree's returned.
Yes.
You could give to run again to generate a fresh value. Is that the idea? What are you going to do with the S trees that are returned?
Oh, I see. What are you going to do with the S trees that are returned? So the idea is that you shrink it.
Yeah.
You then test if the shrunken value is still a counterexample. And if it is, you might repeat the shrinking step again. Right, so you shrink one step, maybe somewhere down, maybe this is compositional, right? So maybe I shrink something over here. I check, is it still a counterexample? If so, great. I will try to shrink again, and now maybe I find something somewhere else. Right, so that's why we...
So you apply run to the shrunken tree to get the shrunken value.
Yes, we get the shrunken tree, we reapply our parser, we get a value out of it.
Okay.
Yes, correct. Yes. Yes.
Right.
Now, please, yeah, questions are very welcome, for sure. Okay, so now let's go back to the example that we had before with the list, right? So we pick a length and then we just generate a bunch of values. So with Hedgehog, we said we had nothing to shrink, right, on the right-hand side of monadic bind because we didn't have a value. But that's not what's happening here. We're not shrinking values, we're shrinking the input to these values. Right, so we have this infinite tree. For monadic bind, what we're going to do is we're going to take the left subtree and use it for the left generator, and then we're going to take the right subtree and use it for the right-hand side of the monadic bind. And now we can shrink these trees independently from each other. So in this particular example, we might have a sample tree that has at the top, this 3 is going to be the length of the list that we choose, and then the values further down are the values from the list that we're generating. And so now we can go back and forth very easily. Right? We can go from this list 1, 1, 0, we might shrink one of the elements in the list to get 0, 1, 0. Now we might go back, maybe shrink the length of the list, get something else again, right? And we can go back and forth between left and right very easily. So this is much better, much more composable, even across monadic bind. So I want to give you some intuition on how you write generators in this way. So prim is going to be our building block. And every time that you write a generator, the thing you have to ask yourself is, how does my generator shrink if the generators that I depend on shrink? Right, so prim is going to take a random number and is going to shrink towards 0. Right, so how do we, for example, make a generator that produces a bool? Well, we just draw a random value in the full range of word 64, and then we just check, is this value more than the halfway point? Right, so that will give us a value either 0 or false, false or true, with equal probability. Right? And now as this value that's produced by prim shrinks towards 0, our generator will shrink towards false. And again, this looks similar to how you might write a generator in other paradigms, right? But we're not writing a shrinker, right? The shrinker is implied. Now, you can get this wrong. For example, suppose that we want to write a generator that produces a value up to a certain maximum. And we might do this simply by taking mod, our maximum, right? Now, if you think about it, if the value that we get from prim maybe shrinks from, say, 101 to 99, and we take mod 10, right? Then our value that we're generating is going to shrink from 1 to 9. It's going to go up instead, right? So that's not a good shrinker. So what you could do instead is, for example, you can write a generator for a fraction, right? So we just call prim, we divide it by the maximum value that prim could ever return. Now you get a fraction between 0 and 1, shrinking towards 0. And then our below, well, we just produce a random fraction, and then we just multiply by our maximum. Right? So as prim shrinks towards 0, the fraction will shrink towards 0, and therefore this value produced by below will shrink towards 0. Yes, question?
Is there a way to write the Boolean generator so that it knows that it only ever has to shrink once?
The question is there a way to write the Boolean generator so that it knows it can only shrink once? Yes, there is. But ask me again if we have time at the end. But yes, we can. Okay, as another example, suppose that we want to write a signed fraction, right? Using the generator that we had before. One intuitive way that you might do it is you just draw a random Boolean and a random fraction, and then if the Boolean is false, it's positive, otherwise it's negative, or the other way around. I forget what I did. This doesn't work very well, because as that Boolean shrinks towards false, we're now going to always produce negative fractions, right? That's not a very good shrinking behavior. Probably we want a generator that shrinks towards 0, no matter where we are coming from. Right, so what we could do instead is we generate 2 fractions and just pick the minimum one. Right? This will give you better shrinking behavior. So people like to say shrinking comes for free in integrated or internal shrinking. Shrinking never is free. Right? You always have to think about shrinking.
Tell me about the 2 fractions again.
So in the 2 fractions case, we generate 2 independent fractions that can both shrink independently.
Yes.
And then we just pick the one that is closest to 0. Yes, question?
I guess you haven't shown us the shrinking of the bind, but I would expect that it tries left and right, and therefore we also get the case where it shrinks the fraction call, even keeping the Boolean true. So wouldn't you also shrink from the negative here?
Yeah, that's true. So monadic bind shrinks on the left or on the right. So you could shrink on the other side, but the moment that Boolean becomes false, there's a very strong bias towards the negative ones. Yeah. Okay. This is a very important example. Suppose that we want to choose between 2 generators. Then what we could do is we just pick a Boolean, and then if the Boolean is true, we pick L, otherwise pick R, right? Now, the problem with this definition is that what we're going to do in this case is suppose that this Boolean is currently true, right? So we're picking L. Now we're shrinking the sample tree with respect to L. Now if this Boolean then shrinks towards false, we switch to using R, but what we're going to do is we're going to pass that very same sample tree that we were using for L before now to R. And any of the shrinking that we did with respect to L might be completely irrelevant for R. Right? So this is not a very good definition. Now, in a way that is fundamental to this approach, right? There's always going to be cases where we use a sample tree in one context and then suddenly reinterpret it in a different context. That's unavoidable in the general case. But Falsify gives you some tools to avoid it in some cases. So this is suboptimal. I want to show you a version that is completely wrong before I show you the proper version.
There's a second problem here that you shrink the Boolean to false and then you stay.
Yes, there's a second problem there too. Yes. So we might be tempted to do something similar that we did before, right? So we just generate both sides and then pick one. The problem here is that suppose that this Boolean is currently true, and so we're using one of the two generators. Then Falsify starts shrinking, and it notices that the sample tree that we're using for R is completely unused, right? Because nobody's looking at it at the moment. Therefore, we can shrink it to the minimal sample tree, right? Therefore, if we then try to switch, the only sample tree that we can run this with is the sample tree that is 0 everywhere, right? If that happens to work, fantastic, but in most cases, that's not going to work, right? So what we want to do, the problem here is that it's not visible to the driver, right, the Falsify driver, that we're making a choice, right? This choice is embedded in this pure function here, but it's not visible to the interpretation of the gen monad, right? What we want to do is we want to prevent an effect from happening, in this case shrinking, when we're not using something. Put another way, we want to selectively shrink, right? We know how to do that. That's a selective functor, right? Which does precisely this, right? Selective functors make that vec that we're making a choice explicit, right? So in selective functors, we have an f of a bool that says which one do we want, and then two generators, well, in this case, two generators, right? And we just pick between them, right? And now we can do and now choose is just if s, right? It has a selective instance, therefore it knows what we're choosing, and it doesn't try to shrink the other part of the tree. So this is a very useful tool that in lots of building blocks.
But we don't want to shrink the bool either, do we? Because then you fix on one tree. You've still got a Boolean generator that will get shrunk to false all the time.
And that depends on your, well, if you have a generator for the bool that shrinks towards false, then your choice is going to do that too, right? But in this particular, I mean, you could have any generator for bool that might toggle, that might, this bool might be generated in lots of different ways, right? It might not have that strong bias. Yes. Okay. There's a very useful generalization that we can make, where we add one little bit of state, and I literally mean one bit of state. What we're going to do is we're going to add to sample whether the sample has been shrunk, yes or no. So the initial sample tree says not shrunk everywhere, and then the moment that we start shrinking, we record that we started shrinking. This gives us just enough information that we can write functions like this, where we have very explicit control over how we're going to shrink. Right? The definition in the paper, but you can imagine that we can just look at the tree. If it's not shrunk, then we're going to give you the x that you want, right, the original value, and if it is already shrunk, we just add enough state into the tree that we can produce the other values here. That's a very useful combinator. For example, we can taking a gen A to a gen of maybe A in this manner. And what we can do now is an answer actually on a question from Simon PJ last year at Haskell'23 when somebody was talking about this hypothesis. And Simon asked, can we use manual shrinking in the context of internal shrinking? And the answer is, yes, we can, with this additional bit of state. So what we're going to do is we have this initial thing that's going to throw away all the sample trees that we have. Like, we just keep the original one. This cannot shrink, right? This is just a generator that can't shrink at all. Then, if we have a tree of values, like hedgehog style, right, we can produce a generator for it simply by using the shrink to, right? We start at the root, and we shrink towards the trees recursively, the subtrees. And now we can provide a combinator that, given a manual shrinker from A to list of A, we can produce a generator by throwing away all the original ways that this was shrinking, reconstructing the tree of values, and then using that. So this gives us a way to embed, if you need to, a manual shrinker. Okay. So I'm not going to talk about in detail on how we generate functions. Actually, it's very similar to how what Koen does in his paper. You have some definition of concrete functions. Nil is the function that uses the default everywhere. We have the way to tabulate functions, which we only do for small functions. And then there's sums, products, things like this, right? And then just like in QuickCheck, we have a class that produces these things. Actually, in QuickCheck, there's two classes. There's co-arbitrary, which a lot of people find quite confusing, and there's function. Here's only one class, and I think it's a more intuitive thing. It just says that given a generator for the codomain of the function, produce a concrete representation of the function for the domain. And Falsify is very carefully designed so that this works, right? That we can generate these infinite structures. These functions are infinite, right? It gives you a value for every possible input because we don't know ahead of time which input you're going to need, right? Only once you apply it to a property, only then do we know, right? And then we can start shrinking, throwing away parts of this thing, and then ending up with a finite description of this function, which is a counterexample. Okay. Should you use this? This is the point where I should tell you, yes, you should all use it. I'm not going to do that. I had the privilege of working with John Hughes a couple of years ago when we were teaching courses on testing before, and I learned so much from John that that completely changed how I think about shrinking. Right? I am obsessed with shrinking. So I think very carefully about my shrinkers. And if you want to think very carefully about your shrinkers, then possibly QuickCheck might be the best choice, right? Because you're very explicit about your shrinkers. But many people are much less obsessed than I am about shrinking for some strange reason. And so they don't want to think about shrinking. And in that case, I think Falsify might work quite well for you because you get an implied shrinker that is probably not as good as a carefully handcrafted shrinker, but it's probably a lot better than no shrinking at all. Right? Now that is the same claim that people make about Hedgehog or integrated shrinking, but then monadic bind has all these cut points, right? So you get a very poor shrinker in many cases. I have no big case studies in Falsify, right? So I have no evidence to say that this actually works, except that in Python it's very popular, right? People in Python really say that this works very well for them. And I would say this is like Python, but better. So I don't know. Yeah, so that's all I have for you. We already have a bunch of questions, but if there's any others, then I'd be more than happy to take them. Thank you.
This is super cool. Thank you. I wonder if, you know, it seems like there's some ways that you can write this where you don't get the shrinker you want, or at least you get a worse shrinker than you want. Have you thought about ways to either statically or dynamically get some information about that?
Yes. Not statically, but I talk about this in the paper and also in the library. There's quite a few combinators in the library that help you precisely to test your shrinking. When people say shrinking is free, no, shrinking is not free. You need to think about this, and you can get it wrong. So the library gives you tools to test your shrinker, and then shrink the counterexamples to your shrinker too. So yeah, I didn't have time to talk about that, but yes, it's in the library and in the paper. Yes.
Very cool, thanks.
So this seems like this is obviously oriented towards shrinking, but it seems like kind of a really nice way to do like composable generation in general. So do you think there's any potential to like use the same underlying data structure, but not just shrink, but maybe do something for like procedural like composable procedural generation or anything like that?
I mean, maybe. Like I don't know whether it really changes anything fundamentally about the generation part.
What's it about, like making it composable and being able to like get the determinism out of it? I don't know.
Yeah, but I mean, even QuickCheck is composable just for the generator, right? It's the shrinker that's the problem. So I'm not sure if this.
Maybe I got to think about it more.
Yeah, thank you though. Yes.
I'm surprised I didn't hear the word monotonic. It seems like there's very sort of order theory, latticey things going on with this and shrinking, especially the shrinking the both sides and the Boolean example where you essentially want like an unbiased product there and not the total order on Booleans. Has this come up at all in your work or?
Yeah, so it's a good question, and I talk more about it in the paper too. But the monotonicity comes from two things. First, the library guarantees that all it ever does, the only way that the library shrinks, is samples going towards 0. Right? And this is one big difference with hypothesis. In hypothesis, you have this, I don't know, there's 14 or 15 different ways that this tree is shrunk and growing, right? And they're proud of it too. Here you have one, right? So it's much more principled in that way. Now, of course, you might still write a generator that is not monotonic, right? Not monotone. For example, the rung below that I showed you, right? Even if the samples are shrinking towards 0, that was cycling through something, right? It was not monotone. So that's one of the proof applications that you have as an author of a generator to get that right. And the library gives you tools for testing it. But yes, it's something that you need to think about.
Great, thanks.
you have time for one more quick question.
Quick. So, in the talk that we had yesterday or the day before,
Yes.
the bit that went from the S tree to the value
Yes.
turned into this bidirectional lensy thing.
Yes.
Do you think, I mean, this is speculating a bit, is that approach compatible? Could you combine that bidirectionality with the stuff that you're doing?
Yes, we talked about this yesterday. It's an interesting question.
Or is it, the selective functors and the monadic binds? That doesn't sound so bidirectional to me.
It doesn't to me either. I am not sure. I think the devil will be in the details there. Also, the fact that this thing is completely, like the emphasis on infinite data structures here too, right? The emphasis on precise treatment of laziness might also get in the way of the bidirectionality. So I think that's an interesting question, but maybe these guys can do another PhD on this or something.
Fortunately, PhD student.
Oh, yeah.
Good call. That's it.
Right.
Let's thank our speaker
Thanks, guys.
again.